first of all, I'm so happy to have this good opportunity to deliver the first talk, especially from the Korean the partners right now. Particularly the first of all, so I really appreciate the good introduction from the Professor Kushua. In particular, I really thank you once again. The orderly coordination from the Santosi. So particularly in this kind of very difficult situation, and this is a kind of very good important moment to share entire the main goal in particular. So the first the environmental cyber, the physical the systems, I'm so happy to present the some of my research the activity, especially in conjunction with the one of the Korean partner, Professor Song Junyoung. So let me go ahead today's generally on the talk from my side. So first of all, so before I get into the main talk in the technical part, I would like to introduce the Korean the poker the point the introduction. I'm working as the sensor and device and system field, especially the PI in the Korean side. And Dr. Song, as you can see here, is working on this circuit and the embedded system for the monitoring system. Also, in International University, Professor Na, also working as the same poker point. One more is the Korean University is the Professor Chodo Kim is working as the very important role in particular the circuit for the analog front end. And the other one is the Sumin National University. The Dr. Che is working as the data processing and the classification the field. All of them are working very hard mode, in particular to achieve the main the goal in conjunction with the Indian side. So as you can see here, here is a kind of the general aims and the objectives for JNC. Okay, so let me just skip on that. I don't want to touch in detail. So now let me move on today's main talk, the progress in the right to frequency convergence circuits based on the low dimensional semiconductor. This work is kind of one of the main research activity which is highly necessary for achieving wonderful sensing environment in conjunction with the novel materials and the circuit level demonstration. So especially in this sense, I will just talk about the general achievement over the future aspects on that. So I'm just working as the poker point in South Korea. So here is a kind of my general introduction. So especially in our group, we are working as several key research field. Number one is the transistor and then the biologging. Mostly they're working as based on the low dimensional material. Number one is carbon nanotube and transition metal dichalcogenide. Another one of the important semiconductor material is the indium gallium zinc oxide. And moreover, we also working on the memories and the perovskite by using the novel electronic material, for example, copper iodide or cesium iodide and a variety of materials. Basically, most of the work is highly specialized in the group with the high flexible electronics technology. So here is a kind of the prologue. So especially the International University is a kind of good time to be introduced. So as you can see here, so International University is kind of the 7.5 hours flight difference from the IIT Delhi and in the capital of India. So our university is located in the very nearby Incheon International Airport. So most people should pass by the Incheon International Airport in order to get in the South Korea. So the university is actually located nearby. So particularly in our university is as you can see, it looks like located on the position and on the sea. Actually, our university is the kind of the built on the reclaimed area. So especially when you arrive at this South Korea, so you should be passed by the international airport, and then the very big suspended the bridge here. So, okay, you can reach it. So here is a kind of the general view for our university, very beautiful scenery. So now here is a kind of the already groups the cover article, mostly the covers the transmitted dichalcosinide application and the application. So here are all of them. Today, so I have to work on the low dimensional material, particularly the 2D materials up to now. So there are many opportunities by using low dimensional material, particularly the insulator, SBN, or a variety of the semimatter or superconductor or semiconductors. In particular, in terms of the semiconductor, because of a better beauty aspect of the low dimensional property and that the physical dimension, we can utilize those kind of wonderful materials for future research activity. So in this sense, among a variety of the materials, particularly the transition metal dichalcosinide is very interesting and very wonderful material for the future electronics. But one of the reasons is the very high thermal and then mechanical stability, also the excellent electrical property with the size of the band gap. That is kind of one of the main point. So moreover, I mean, in particular, the molybdenum disulfide is kind of very high opportunity for the number one is the field effect transistor, memory cells, and gas sensor, and the photo detectors. So still, these materials have the utilized for electronics. I mean, a variety of research activity has been introduced in the literature. But however, the practical effects on the TMDC is still very foggy, like the London fog. So here is kind of one of the limitations, even though a tons of research papers are published up to now. So in this sense, what is a killer application? So this is very important. So in this sense, I have the work on the key challenging issues for the best application. Number one is the key motivation can be introduced. Number one is medical application or automotive application. The other one is the IoT application, particularly the bioimaging or optical devices, for example, the LiDAR or the IoT security issues. All of the applications require very high level of external noise disturbance leading to the critical damage is kind of one of the very critical aspects. Particularly in order to avoid some critical damage, we have to guarantee very high level of signal to noise ratio. That is a kind of a core requirement. So in this sense, the optoelectronics, and as compared with the conventional material, so the low dimensional material, for example, the molybdenum disulfide is wonderful in terms of the size of energy band gap. Moreover, we also have very novel property depending on the number of layers. I mean, the size of the energy band gap can be changed according to the number of layers, and that is a kind of very another important property for future research opportunity, particularly circuit level demonstration for optical application. So as you can see here, the different photodetectivity according to the number of the molybdenum disulfide has been explored. So in this sense, we can fully take advantage of those kind of property in terms of the energy band gap dependency according to the number of the layers, which can be fully extended toward the electronic application. So here is a kind of the core motivation, the right to convergence circuit. Typically, most of the optical sensors can be detected as the passive mode. Because of that, I mean, that is one of the core limitation, in particular the poor signal to noise ratio, and then hard to convert the signal. So that is a kind of limitation. So however, so when you utilize those kind of circuit levers by using the novel concept, I mean the directed the right to frequency converter circuit concept. So that means we can immediately change the right information to frequency level. That means we can improve or achieve much more high level of noise immunity. So that is kind of one of the core of the motivation why we have to consider right to the frequency conversion circuit in order to achieve the external noise immunity. So in this sense, I mean, the photosensitive ring oscillators are core elements. So in order to achieve those kind of application and then the target goals, how can they achieve the photosensitive ring oscillator? So here is a kind of core the motivation here. So in this sense, I mean, the right to the conversion scheme is so like that. They typically as per the conventional schemes, they utilize the closed low pass filter and the low filter, and the voltage control the ring oscillators are one of the core platform. However, if we just develop the photosensitive inverter, and then the ring oscillator can be implemented by connecting the odd number of the inverters. And for the case that we can easily achieve the photosensitive ring oscillator, or leading to getting the output, the information as the frequency of the domain. So that is kind of one of the key motivation, and then the core of the scheme. So particularly with this kind of application, we can also consider the Internet of the Things. That is kind of one of the core motivation. To prepare for the trillion sensor error. So moreover, I mean the ubiquitous sensing in the data line is a kind of one of the more important opportunity, particularly the more regional and more practical the concept. So now as compared with the single transition, as I told before, and typically there are poor property, the poor the signal to noise ratio, and moreover the hard to convert the signal to system level. So, but however, if we implemented the entire system by using right the frequency conversion circuit, so with the high noise immunity can be easily achieved. That is a kind of core motivation and the direction which we need to achieve. So in this sense, the right to frequency conversion circuit is kind of the flexible device, and low dimensional materials can be easily combined in order to achieve the next generation of the IoT sensor platform. So now, with this kind of platform, we expected that the very high effectiveness in terms of high network security. Number two is low power consumption, as well as the high chip density. Those kind of the core aspects are one of the killing aspects of which we need to consider for the future opportunity. So let me move on. The photosensitive, the complementary circuits based on the recently we introduced the multi-layer, the lithium sulfide and the carbon nanotube transistor. Typically, there are many kinds of the transition metal dichromate. However, as per the lithium disulfide is a kind of very interesting property. So typically, the and its bending gap is not too much affected by the number of the layers of the lithium sulfide as compared with the other transition metal dichromate. So moreover, it has very wonderful high mobility as well as the good electrical property in conjunction with the photo detectivity. So those kind of materials can be implemented toward the complementary circuit, particularly by using the p-type property. So now, the key concept is by using the lithium disulfide and then the different p-type property coming from the carbon nanotube, we can achieve the feature the high efficiency photodetectors, as well as the achieve the photosensitivity, uniformity, and air. That is kind of one of the key motivation. Number one, they work, and then those kind of the gallium sulfide can be utilized as photodetectivity. So those kind of work are already reported in the literature. So with this kind of scheme, we can also extend it, the N-type gallium sulfide combined with the P-type, the carbon nanotube, which has the low sensitivity of the photodetectivity. So in this sense, I mean, here's a kind of the summary for the previous report in the literature. So basically, the starting point is the 2009 and the electron device radars. In this, at that time, the photosensitive inverters has been achieved by the alpha silicon technology, and then those kind of technology can be extended toward the molybdenum disulfide, and then with the light silicon layer. And then in order to avoid the light silicon layers, we can also adopt the N-type, the gallium nitride activity, which has very high energy band gap in order to achieve the low sensitivity of only the exposure region. So moreover, so another the key point is, as compared with the N-type or the depletion load or enhancement load, the base of the application. So we also need the much more low power consumption by using the MOS2 and MOKE. That is a kind of one of the research achievement up to now. So here is a kind of the fabrication and device demonstration in conjunction with the gallium sulfide as well as the carbon nanotube or the process pro. So with this kind of the configuration, the red one is the gallium sulfide is the N-type region, and then the gray region is the carbon nanotube. The complementary circuit can be implemented here like that. So with this kind of way, we can achieve the complementary circuit. So with the different wavelengths, the blue and blue to the left, we can detect all the different wavelength activity according to the different wavelengths. So here is a kind of the data, the gallium sulfide and the carbon nanotube transistor. But typically, we achieve very wonderful the N-type, the gallium sulfide transistor, and then on the right side is the carbon nanotube transistor has achieved as the P-type property. So interestingly, as per the gallium sulfide, as we expected before, so we observed the very high photodetectivity according to different wavelengths. However, as per the carbon nanotube, so the sensitivity of the line is fully negligible. That is coming from the tight banding mechanism because of the high the binding the energy leading to only the generation of the extron. It's not the leading to the making of the free electron in the holes, and that is kind of the reason why we haven't got any kind of photodetectivity for the carbon nanotubes. So in this sense, the very high sensitivity, the gallium sulfide for N-type branch, by using the carbon nanotube, we can achieve the P-type, and then N-type, the complementary circuits can be easily achieved. So with this kind of way, we entirely explore the photo responsivity and responsivity to the wavelengths, all of them. So we achieved very wonderful property in terms of the photo responsivity and the detectivity. And the next one is we also check the entire voltage transfer characteristics under the right illumination, and the road line analysis has been performed here. So with this kind of different the wavelengths, the red and the green and blue, we achieved the entire different voltage gain and the wave dependent transfer characteristics here. So with this kind of data, we achieve the entire power level and according to different wavelengths here. So now let's move on SPICE simulation based validations. The carbon nanotube and the gallium sulfide is nicely replicated here by using the Cell-Baku, the RPM model. So now with this the SPICE on the model, we fully replicated the ring oscillator based property. So as you can see here, the wavelength is reduced, or the oscillation, the frequency is also the increase. This is kind of the one of the indication of how we can achieve like the frequency conversion circuit here, according to the different wavelengths. So now let's move on the much more scalable complementary circuits by using the low dimensional carbon nanotube, as well as the very commercialized the anti-carbon indium gallium zinc oxide. So especially the indium gallium zinc oxide is one of the very beautiful material which has been the commercialized recently. So display application, high scalability, and the tunable performance by using the different target materials we can achieve. So with this kind of background, I mean, we intentionally control the photodetectivity by changing the annealing temperature, leading to different the oxygen vacancy, the level. So typically the most of the research has been focused on to eliminate completely the oxygen the vacancy. But however, for the application of the photodetectivity and the latitude conversion circuits, we needed to secure, number one is the relatively acceptable the photosensitivity according to different wavelengths. Moreover, the complementary circuit levels are necessary. So in order to achieve scalable property as well as the different the photodetectivity, we achieved entirely the anti-reason is coming from the indium gallium zinc oxide, just only changing the annealing temperature for the control of the oxygen level. But however, the p-type reason, so the carbon nanotubes is fully adapted to achieve the light insensitive property. So with this kind of scheme, we fully validate the different annealing temperature effect as well as the different wavelengths depending on the detectivity properties nicely secured here. So now let's move on the one of the property for the express analysis for indium gallium zinc oxide according to the annealing temperature. As you can see here, when just only adapted to 100 degrees Celsius, there are so many defect states generated inside. So because of that, there are some the severe photoresponsivity is achieved. However, when you utilize the 400 degrees Celsius, so oxygen vacancy is dramatically reduced. Because of that, the anti-property is guaranteed. However, photosensitivity is dramatically reduced. So now, in between certain conditions necessary, so we adopted the 300 degrees Celsius. So with this kind of condition, as you can see here, the 400 degrees Celsius, the right frequency conversion property is negligible. However, 200 degrees Celsius, I mean, the photosensitivity is very amazing. However, in terms of reliability, is very poor. So we have to choose the trade-off reason at the 300 degrees Celsius. With the entire scheme, we fully validated the circuit level demonstration. So now let's move on the final, the flexible light frequency converter circuit. As you can see here, and this is a conversion scheme, and then the RZB properties achieved. So now let's move on the electrical characteristics for complementary circuit here. So individual the TFT level is critically important to understand the circuit level demonstration and the performance validation. So on the right, on the left side, on the top, as you can see here, the violet color is the p-type property, and then the orange color is the n-type property. So IGZO TFTs can show very high on-off ratio, whereas the acceptable the current level. As per the p-type property for the carbon nanotube show us the wonderful the p-type property. So key here is, so by using the carbon nanotube p-type, the n-type range of the IGZO, we achieved fully working the complementary circuit. So moreover, the Landover NOR based logic gate is where they explored and then implemented here. So all the properties nice replicated here to achieve the wonderful the logic the functionality. So in addition, the three-stage linear oscillator is fully implemented here. So with the compounded inverter properties, we also got the experimentally obtained the linear oscillator property. Here's the entire data. So with the scheme, so the transfer and the output characteristics for n-type p-type cap is under the right elimination. So here's very good news is the as per the ICU cap is, as I told you before, we got the different like the responsivity according to the different wavelengths. From the dark is the right side, and then as the wavelength is reduced from the dark to the blue, right? So as you can see here, the photo responsivity is also increased, and the photo leakage current is increased. With this kind of n-type reason, we can utilize for the direct frequency conversion circuits is the core part. Moreover, the p-type, the carbon nanotube, fully different behaviors observed. So the only the insensitivity of the right response was achieved due to the very strong binding energy in the carbon nanotube, which is coming from the low dimensional carbon nanotube property. So with this kind of the load-oriented scheme, we fully implemented the red and the green and the blue and the different responsivity here. So also photodetectivity also we achieved according to different wavelengths here. So now the next one is the photo behavior for right choose conversion circuit under the right illumination is very important. So on the left side, as you can see here, the inverter is fully replicated and then achieved the voltage transfer characteristic shift according to the wavelengths. Yeah. Moreover, the linear oscillator data is, as you can see, load the waveform according to different wavelengths is achieved. So next one is the oscillation frequency and the gain property. So right illumination property is the increases. I mean, actually the wavelength is reduced. I mean, entirely the photoresponsivity. So the oscillation frequency is the linearly decreased. I think that is a kind of very important point. Moreover, the oscillation frequency increased, and however the gain is reduced. I mean, with this kind of linearity is very, very important for circuit implementation and achievement. So next one is the here is the entire system which we implemented, like the frequency conversion circuit based on the complementary circuit here. So here is the kind of cross-section view, and that is all the flexible devices implemented. Then this is the entire system. I think this is kind of the cover article which has been published recently, 2021. Especially this work is some of the collaboration with the Professor Songs. I mean, we work on the low dimensional material based inverters and the circuit level is demonstrated. Moreover, in order to achieve the highly integrated flexible electronics, so we need much more high the level of the circuit. Typically, those kind of circuits should be implemented the commercialized circuit. That is kind of the best way. I think one of the method is we deployed the 64 nanometer and technology node for the implementation of the frequency to conversion digital circuit. Especially the oscillation signal can be changing into the discharge mode the data. I think those kind of the data has been achieved by using the foundry service, and then those kind of chip can fully integrate together with the linear oscillator, photosensitive, the linear oscillator, the scheme. With this kind of way, so we can fully integrate it high level the silicon, the chip based the signal processing part is the built-in and the entire system. Moreover, the low dimensional material-based the sensing the scheme for the light to frequency conversion circuits wonderfully be implemented. That is a kind of core aspect. So this is kind of one of the first demonstration to combine with all flexible circuit as well as the highly integrated, the high performance of silicon technology. That is kind of one of the future direction which you need to be consider. So now let's move on the future aspect of the light to frequency conversion circuit based on the low dimensional material. So with this kind of the application, we can consider number one is the medical application, especially the SpO2 measurement, particularly bio application. I mean, the SpO2 level is a kind of the oxygen level in the blood is very, very important. With in this sense, the typically we can detect the oxygen level by detecting the light absorption the property, particularly on the near IR or the blue light reason. So that is a kind of the one of the highly integrated medical application opportunity. Moreover, another opportunity is biological, the multifluidic systems, one of the another application. The number three is the agriculture and auto detecting the control. I think this is kind of one of the future the opportunity which can be implemented in India or the South Korea, particularly for advancement of the agriculture part. And typically, the auto the control is very important, but typically the how can achieve such kind of the implementation much more cheaper the cheap cost, moreover the high performance and the highly integrated mode with the fully the reliable platform. And in this sense, the agriculture field, I mean the light to frequency converter circuit can be fully implemented. I think that's a kind of the opportunity. So next one is the optical feedback system in the display is a kind of the very important for the virtual reality or augmented reality. I mean, that is a kind of the full aspects of future the opportunity can be utilized for the light to frequency conversion circuit. Okay, so let's let me the summary and today's post. So we I overview the photosensitive the inverter for the application of the light frequency conversion circuit, particularly the MS2 or armor silicon techniques also can be compared over the performance, the integration, power consumption on the part. The MS2 is one of the very important the core part for the future opportunity, in particular the implementation of light frequency conversion circuit. So moreover, I mean the other approaches is the high energy bandwidth gap, but gallium nitride is also one of the opportunity. So furthermore, I mean the complementary circuit should be the one of the core parts which you have to implement it. So in this sense, by using the low dimensional material in terms of the minimize the sequence or fully flexible, and then those kind of property can be also achieved by using the MOT or RES2. The MS2 is one of the example, and the carbon nanotube and the IGGO techniques are also the very nice matching for achievement of the wonderful, the fully flexible and the high performance over the the capability to combine with their highly advanced silicon technology. So moreover, I mean this kind of platform can be utilized, but one of the examples is the bio application for sensing the SpO2 sensor, and also the agriculture, the field, over the bioimaging or the interactive the displays can be the future opportunity. So now lastly, I would like to recognize the acknowledgement by the group members. So as you can see here, in our group, I mean, there are many the wonderful Indian researchers. One of the Mokurula and the Niraj, and then the Azid and the Daranze, and all of the PhD students, postdocs are one of the core researchers in the group. I think this is kind of one of the put the example of how we can work together, particularly between the India and the South Korea for the better research opportunity, moreover the future prospects in terms of the better both of the countries the research opportunity and then the benefits. I mean, this is one of the result. I mean, okay, now it's time. I really appreciate.